All right, well, let's get started. We're going to be talking about water softening today. And just a reminder, we don't have class on Friday of this week because of, what's it called? February break. Yeah, so we've got February break. I've pushed back the deadline for homework 5 until Friday at 1, so you've got an extra 48 hours for that one. Because I wanted to talk about softening today, and we'll go through an in-class exercise that kind of shows you how to distinguish carbonate hardness from non-carbonate hardness and so on. So please upload your homework number 5 to Blackboard before 1 o'clock on Friday. And then the wastewater treatment tour, just a reminder that that'll be Wednesday the 12th, so 1 month from today. We'll be enjoying the aromas and the visual splendor of the wastewater treatment plant. So for that, if you want to bring a mask, you're certainly welcome to. Maybe help you to keep the floating wastewater particles out of your face. I've heard from people who work at wastewater treatment plants that the first couple of weeks that they work there, sometimes they'll have like a low-grade fever a little bit, but then they're like bulletproof. Just the constant exposure to a little bit of microorganisms from like the mist and something. I've never gotten sick or any kind of a fever when I've toured, but anyways, we're going. Today we're going to be talking about softening. It comes from section 3 of chapter 6 in your book. It's actually, I think, one of the most nicely done chapters in the book, or sections in the book. Is it's making a kind of an abstract concept pretty understandable with the examples that they've got in there. So I'll make another plug for the value of taking time to look over the resources in your book. I think that there's a lot to learn from that, and it'll help you to understand and do the homework assignments a little bit more quickly. So one topic that kind of straddles both flocculation and softening is something called an upflow solids contact chamber. And I'll show you a diagram of one in just a minute, but this is just a way of combining a clarifier, a mixing basin, and a place for flocculation to occur in a single footprint. So it's kind of just a clever idea that upends our normal assumption, which is that, ordinarily in a settling basin, we'll talk about settling basins in detail, but the place where we take the water after flocculation, ordinarily we'd have the water coming in through a pipe, and it's flowing along towards some outlet, let's say, and the water's going out. So a particle is settling down at the same time that it's moving to the side. So the bulk flow of the water is going towards the outflow of the clarifier, and the particle is settling down. In the case of an upflow solids contact chamber, instead of having the water flowing sideways, you have the water flowing up while the particle is settling down. And that has some interesting advantages because as the particle is settling downward, it might encounter other flocks and combine. And it's also a way of saving construction costs by combining a couple of things together at the same time. So I'll show you the diagram, and that'll help us to understand these relative advantages. But we would ordinarily use upflow solids contact chambers in situations where we don't expect there to be huge seasonal variations in the water quality. So groundwater would be good. Surface water might be okay if we were taking from maybe like a high altitude lake where we don't expect a lot of changes in the temperature and the turbidity and the nutrient content over time. And then the other limitation is that we have to size these upflow solids contact chambers so that the particle settling velocity that you'd expect is greater than the fluid velocity that's up. So like I said, this is especially important when we're talking about softening today, because this is a kind of device that we could, in this, if you follow the direction that the water's coming in. So this is a circular tank that we're looking at a cross-sectional view of it here. And so if we were looking at it from the top, it would just look like a circular pool of water. But now with this cross section, water comes in, and this influent may even just be the raw water that hasn't been treated at all yet. And when it comes into this central area, which is shaped a little bit like an open at the bottom Erlenmeyer flask, so as the water comes in, there is a lot of mixing in the central section here. And so zone A, it's showing as rapid mix because we'd be feeding in chemicals with a high intensity of mixing. And then as the diameter of this central zone is increasing, what that does is it slows down the velocity of the water. So we're gradually tapering the velocity down so that we don't disturb the flow set up here in the main upflow and sludge blanket zone. So as the diameter is increasing, that's also a chance for the gradual reduction in mixing energy that we associate with what's happening in flocculation. Remember that we want the flock to get gradually larger, and so having the diameter increase is increasing the cross-sectional area, and it would therefore be reducing the flow rate. And you can see that if you've got an increasing cross-sectional area, but the central shaft is rotating at the same speed, that's just a way of reducing the mixing energy. And so the G value, the velocity gradient, would be going down. So by the time the water exits this kind of central bell structure, the water has had a coagulant mixed in, flocculation has occurred, and these particles just now need to be settled. And so the water is flowing up, and the particles are settling down. And then there's this slow moving, kind of like a squeegee at the bottom. This sludge scraper is just any sludge, which is like flock plus hardness chemicals that are precipitated, that settles to the bottom, is just swept and accumulated into a central sump area where then it can be drained out and dewatered and disposed of. So then the clear water, which is finished and has no or very little turbidity now, goes to the top and exits through a series of weirs. And so I think I've showed you some pictures of a treatment plant that I visited in Indiana. Let's go back to that. So these are circular upflow clarifiers, and then when the water gets to the top, it goes over the edge with a series of weirs like this that keep the velocity low. So we'll talk more about settling in general, but this is a special case of settling which is applicable to softening. So I wanted to introduce it today. So let's just talk about water hardness and softening in general terms. Hardness is caused by polyvalent cations, and the polyvalent cations we're accustomed to seeing in water predominantly are calcium and magnesium. Those are the cations that would be in the highest concentrations. There may be a little bit of iron in water, like I've seen at the groundwater source in Indiana where I did some research for my PhD. Their iron concentration was astronomically high, and it was only about 5 milligrams per liter. In comparison to calcium may be well over 100, magnesium may be 50, or even approaching 100 in some cases. So iron is much smaller contributor of hardness. Manganese is even less than iron typically, but technically they are polyvalent cations, and so they do contribute to the hardness. But from a functional standpoint, when we're thinking about how we want to improve the chemistry of the water and make it more useful to people and more aesthetically pleasing, what in practical terms we're trying to remove is calcium and magnesium. And the reason why is that hard water it doesn't feel very good. When you're showering in it, it reduces the efficiency of detergents to clean clothing and dishes and automobiles. It makes it so that your soap won't lather in hard water. And so if you've ever bathed in soft water, you'll instantly feel the difference. It feels like just the water is more slippery. And in fact, anytime I visit my parents who have very, very soft water, I almost feel like it's a little bit dangerous in the shower because the bottom of the shower gets really, really slippery compared to just the normal water that I'm accustomed to. The Ohio River water that we've got, it's not particularly hard, it's not particularly soft, it's just kind of in the middle. But you'll know it if you ever shower in truly soft water because it just feels like it's almost impossible to get the soap to rinse off because it lathers so well. That's soft water. Another factor, maybe a little bit more engineering related, is that when you've got hardness in water, it can accumulate in pipes and especially on water heaters because the calcium component of water hardness has inverse solubility with heat. Most inorganic constituents, most salts, most minerals become more soluble in hot water. But calcium carbonate is the opposite. It's less soluble in hard water. So you've probably noticed before that if you boil water in the same pan and you don't rinse it off, then there's going to be like a white flake or some scaling that accumulates on it. And that is because of the inverse solubility of calcium carbonate. And so that same precipitation could accumulate on the heat exchange elements of your water heater. And it can also accumulate in pipes. And so here's an example of a fitting that has had the deposition of hardness minerals. Here's a water heater where the little resistant heat exchange elements have been completely coated with calcium carbonate, and it's less efficient at transferring heat when the heat exchanger has a mineral completely coating the metal parts there. So how does water become hard? Like, think about the water cycle. Water originates from the sky with rain. It falls down onto the surface of the earth, and then some of the water will run off, and some of the water will go into the ground. And so the rain that is falling on the surface is relatively acidic. You know, even in the absence of acid rain, which is caused from coal that has sulfur in it, just water that's in contact with the atmosphere has a little bit of carbon dioxide dissolved in it, and that makes it slightly acidic. And then the water that's entering the topsoil may pick up a little bit more carbon dioxide because of bacterial action that happens in the vadose zone of topsoil. So in the zone of aeration, where there's a mixture of moisture and air and bacteria, they can give off a little bit more CO2 that further suppresses the pH of the water, makes it acidic. So that the water that's getting into the soil, if it has a low pH, it's going to dissolve some of the minerals that may exist in the soil. And so depending on the type of soil that you have, there may be limestone in the soil, which is rich in calcium, rich in magnesium, and the water seeps through the cracks of the limestone. It picks up the chemical characteristics of the soil, and that can include hardness. So the place that we see extraordinarily hard water is where they've got a lot of limestone in the subsurface and where they're using groundwater sources. If they're using surface water, like water from a lake or from a river, then they're generally not going to have as much water hardness as wells. So any questions so far about what it means to have hard water or what the implications are? So we want to get that hardness out because if there's too much of it, it is damaging to the pipe infrastructure, it's damaging to water heaters, it makes it so that soaps and detergents don't work, it makes it so that people feel kind of scaly in the shower and have that unpleasant sensation. We want to remove excess hardness. And what we do to remove hardness is changing depending on how much hardness there is and what the source of it. So the easiest way to remove hardness is to first take out the calcium. And the reason why I say easy is just calcium precipitates first. And both calcium and magnesium, the way that we get that out of the water is, remember, it got into the water in the first place because the water was a little bit acidic. And the lime would dissolve into the water under low pH conditions. And so what we need to do is reverse what got the hardness in the water in the first place. And so if what got it in the water in the first place was acidic conditions, then we want to make the water basic. We want to take it from its slightly acidic into the basic range. And so if we raise the pH to 10.3, what we can do is we can draw out the calcium, and the calcium would form with carbonate, and it would precipitate into calcium carbonate. And then if we take the pH a little bit higher, then we can get magnesium hydroxide to precipitate. So there's something called speciation, and there's going to be a balance between the solid and the dissolved components of a species. And at 10.3, it's in favor of the solid fraction of that equilibrium for calcium carbonate. For magnesium hydroxide, it's 11, that you have the preponderance of the minerals being solid. There will still be some calcium, there will still be some magnesium left behind in solution, but our hardness will be improved dramatically if we can just raise the pH of the water. So because the calcium precipitates earlier, meaning like if we're adding some sort of a base, if we're adding a base to raise the pH, the calcium precipitates first. It uses less chemicals to do that. And so we think of it in terms of cost. You know, as engineers, we're trying to achieve some outcome most efficiently, and we're trying to save the client money, and we're saving them on the chemical budget when we focus on removing calcium rather than magnesium. And hopefully we can get as much of the hardness out with as little of the base as possible. Actually, when we start to add a base and increase the pH, there's a sequence of things that happens. And calcium isn't the first thing that's removed. The first thing that's removed is the acid that is in the water by virtue of equilibrium with carbon dioxide. So just like an initial fraction of the lime that we add as a base is going to be used up neutralizing the carbon dioxide. And then after that it's calcium, and then it's magnesium. But then the other thing that's happening as we're increasing the pH is that this speciation, which is just the relative preponderance of either bicarbonate or carbonate, HCO3 minus is called bicarbonate, and as you increase the as you increase the pH into the basic range, then bicarbonate is converted into carbonate. And it may be that we use up all of our carbonate through precipitation. So there might be more calcium in solution than carbonate. And so we're going to, when we get some water chemistry from the lab, we'll do some calculations to figure out how much of the hardness that's there is associated with carbonate and how much of it is associated with non-carbonate. Because ironically, what we may have to do in order to get the calcium to precipitate is we're going to add more calcium, which is really counterintuitive, that the thing we're trying to get out of the water is calcium, but the way we get it out is by adding a different kind of calcium that increases the pH and causes the precipitation of calcium carbonate. And then the other thing that's counterintuitive, besides the fact that we're adding calcium to remove calcium, the other thing that's counterintuitive is that sometimes we have to add carbonate so that there can be an anion for the calcium ion, which is positively charged, to latch onto. Okay, so let's talk about the chemicals that are used in the softening process. Calcium hydroxide is one of the options that we have available. It's called hydrated lime. You know, if you go into the chemical market and you're going to try and buy the chemicals that you'd need for a wastewater or water treatment plant, then hydrated lime would be one of them. And it raises pH because you can see here it's a base, calcium hydroxide. So the irony, though, is that it includes calcium. So it will precipitate. Don't worry about that. We're going to get more calcium stripped out of the water than we're adding. But it's just always a little bit odd to think that, we could add, for example, sodium hydroxide, and that wouldn't contribute to hardness because sodium is monovalent. It's just got a +1 charge. But sodium hydroxide is way more expensive than calcium hydroxide. And so sodium hydroxide would never be used in water treatment just because calcium hydroxide is more abundant. So it's a cheaper way of increasing the pH. But even cheaper than hydrated lime is quicklime. And sometimes it's just called lime. So calcium oxide. So what calcium oxide does is when you add it to water, it turns into calcium hydroxide. So hydrated lime has already been turned into a liquid, whereas calcium oxide, you can buy that as like a solid chemical. You put it in the water. It gives off an enormous amount of heat. It's very exothermic, and so it's one of those reactions that we have to be a little bit cautious about in the water treatment plant because it could, in theory, cause the water to boil, or if you add it too quickly, it could cause the water to splash all over the place. And this is basic, so it's dangerous. If it gets in somebody's eyes, it could cause irritation to the eyes. It could cause damage to the skin. And so, we're not playing around with these softening chemicals. It raises the pH and it's cheaper than hydrated lime. And it's also, in terms of like shipping expenses, it's going to be a lot more compact. So you get more bang for your buck with quicklime. So adding calcium oxide turns into hydrated lime, and then that is going to increase the pH. Now the other chemical that we may have to use, depending on how much carbonate is in the water, is sodium carbonate, sometimes called soda ash or just plain soda. And soda is providing the carbonate that, like if we've got so much calcium and so much magnesium, but then maybe it's sulfate as the anion that's in our raw water, then there wouldn't be enough sulfate, and the solubility is higher for calcium sulfate and magnesium sulfate. So it's just easier for us to strip the water out if there is carbonate for the calcium and the magnesium to latch onto. So sometimes we have to add sodium carbonate. So here's a look at the reactions that occur. The first thing that happens when we add hydrated lime is that the carbonic acid is neutralized. And right now, if you had a glass of water sitting on the countertop and it had been in contact with the atmosphere for a couple of hours, then there would be carbonic acid in the water. And it's just when atmospheric carbon dioxide is in contact with water, then a fraction of that will dissolve into the water and speciate into carbonic acid. And there's not a lot of it, and it doesn't have a huge effect, but still, when you add the lime to water, a portion of it is going to be burned up, just neutralizing that carbonic acid that's in water. So that's kind of the first thing that we have to overcome. And this is not going to cause any softening effect. So you're losing a little bit of your lime up front just to neutralize the acid that's in the water because of equilibrium with atmospheric carbon dioxide. Then once you've overcome that and you continue to add more lime, then you're starting to increase the pH to the point to where the calcium that is in solution, this is the hardness calcium we're trying to get rid of, is going to precipitate into calcium carbonate. So you look for every 1 mole of calcium hydroxide that we've added, we can get out 2 moles of calcium carbonate. So the original calcium that we added is going to be swept out, and then it's also going to take one of the calciums that was contributing to hardness along with it. So that's a good thing. And then the solid precipitate, we can just get it to settle in the clarifier that's downstream. So, we may be doing softening and flocculation simultaneously, like in the solids contact basin that I showed you earlier today. And if that's happening, it's kind of an enhanced effect. It's synergistic because the precipitation is also grabbing onto flocks of colloid chemicals and helping to improve the turbidity that way. So hardness by itself doesn't contribute to turbidity because it's dissolved chemicals, but getting the hardness out can remove turbidity that kind of synergistically. So this is the second step, is removing carbonate hardness due to calcium. Next, let's say we continue to add more of the hydrated lime. Then, once we've exhausted all of the calcium that's going to come out, that's when you start to precipitate some of the magnesium out. So it's forming magnesium carbonate and calcium carbonate. So the calcium carbonate, one calcium, where did that come from? It came from the calcium hydroxide. But then there was another magnesium that gets taken out, and you can see it's consuming alkalinity as it does that. So the HCO3, the carbonate, is going to be used up. And we can only have this reaction if there is some carbonate in the water. So if there's not carbonate in the water and we want to get rid of the magnesium, then we'd have to add the sodium bicarbonate and also the hydrated lime. Okay, so you can get magnesium hydroxide as a precipitate. So this is the step where if we add the sodium bicarbonate, then that is what we're referring to as the non-carbonate hardness, and the pH would still be high. We wouldn't need to add any further quicklime to get the non-carbonate hardness out. It would just be us adding the source of carbonate so that the calcium, which is ready to precipitate as soon as there's something for it to latch onto, the carbonate for it to latch onto. Once you provide that carbonate source, then it'll precipitate. And then there could be the removal of magnesium with non-carbonate hardness by continuing to add more of a carbonate source as well. So these are the chemicals which we could use to increase pH, and our book explains that adding soda is the source of the carbonate, and we're also having to overcome the dissolved carbon dioxide. So just kind of a summary of the same things that we've talked about here in this slide. But this bar chart is an important way of visualizing it, and this is where we finally get to make use of this notion of as calcium carbonate. You remember earlier what we did is we converted amounts as the species into amounts expressed in terms of as calcium carbonate. And its hardness calculations and alkalinity calculations are some primary areas where it's beneficial to us to express everything in terms of as calcium carbonate, because then it tells us how much of the chemicals we need to add regardless of what species is there. So this illustration is just showing what if we had a known amount of carbon dioxide in the water. So here this is saying we've got 29.3 milligrams per liter of carbon dioxide as calcium carbonate. So that isn't necessarily contributing to the hardness, but it's on this chart anyway because it's going to be influencing how much of the hydrated lime we have to add, for example. You can see here that the concentration of the calcium, 149.2, is on the top part of this chart. So this bar chart is showing the cations on the top part and the anions on the bottom part. And they should be the same length within, 1%. If they're not the same length, then we don't have all of the relevant species data that we need to know. There should be a balance between positive charge and negative charge in solution. You can't have more plus than negative in solution. There has to be a balance between the two. So the overall length of the cation component of the bar chart is the same length as the anion part. The carbon dioxide bridges both the top and the bottom because it's not an inorganic like speciating cation or anion. It's something else, carbonic acid. So we've got the calcium takes us from 0 to 149.2. And the reason why calcium is first is because it's removed first when we're doing the softening. And you can see magnesium, the length of it is 65.8. So that goes from 149.2. If you add 65.8, then that takes the total charge of positively, of the cations up to 215. And then just for charge balance, we add the sodium on top of that, but we won't be removing sodium. Sodium doesn't contribute to hardness in the water, so it's not a target of the softening reactions that we're going to be doing. Now, graphing the amount of bicarbonate in the solution allows us to see how much of the hardness is carbonate and non-carbonate. So hardness overall here is the total sum of the cation species. And so there's 215 total milligrams per liter of hardness because that's the calcium plus the magnesium. So how much of it is carbonate hardness and how much of it is non-carbonate hardness is what we may want to know. So here the carbonate hardness is 185 because you can see that here's the carbonate component from 0 to 185. And so then the non-carbonate hardness is the total hardness overall minus the carbonate component of it. So 215 minus 185, there's 30 milligrams of non-carbonate hardness according to this bar chart. Now, how much can we actually remove? One of the interesting things is that even after our precipitation reactions, we're often going to assume that you leave behind 40 milligrams per liter of carbonate hardness because of maybe incomplete mixing of the chemicals or just the speciation and the there's even at a pH of 10.4 or 11, even at those elevated pHs, there's still going to be a certain fraction of the calcium that is left behind. So I'll show you how we account for that 40 milligrams per liter when we go through the in-class exercise. Let's do that now. Now, there's a flow chart here that's kind of interesting that can guide our decision-making process when it comes to how much of which chemicals to add. But in addition to that, I wanted to show you that I'm asking the questions in a certain order on the in-class exercise today. That I'd like you to start by just going through the questions in the order that I'm asking them and then double check with the flow chart like this figure on the right-hand side. So let me just open it up and I'll give you these papers in a second here. So what you're going to do is prepare a bar chart similar to what I showed you just a minute ago where you've got the carbon dioxide on the left side, you've got the cations on top, the anions on the bottom. And then we want to determine how much of the hardness is carbonate, how much of it is non-carbonate. And we're going to figure out how much lime is required and then how much soda we would have to add if we want to soften the water to 85. We're not trying to get the water to like 0 milligrams per liter of hardness. We just want to get it down into the range that people would consider it aesthetically comfortable, pleasing. You know, like right now, how much hardness is there? There's 333 plus 78. So we're into the 400 milligram per liter range, which would be considered very hard. And we'd like to take it down to below 100. So 85 is our target. So the first step here is just to make a chart that looks similar to the formatting of this one, where you've got calcium, magnesium, sodium on the top, bicarbonate, sulfate, and chloride on the bottom. And then on the left side is the carbon dioxide. Okay, so first things first, when we make the bar chart, we want to illustrate how much carbon dioxide there is, because we're going to have to neutralize that. And then it's not part of the hardness though, so that's why it goes on the left-hand side of the figure. If we want to calculate the hardness, it's just here from 0 and to the right. But the overall length of the chart may reflect how much lime we're going to add. So the carbonate hardness is the overlapping between how high is the hardness. So hardness goes from 0 to 411. All of that is hardness. The carbonate portion of the hardness is from 0 to 277, and then the non-carbonate portion of the hardness is from 277 to 411. So there's 277 milligrams per liter of carbonate hardness and 134 milligrams per liter of non-carbonate hardness. All right, so that's A, B, and C. For D, it says find the amount of lime that's required. So how much lime are we going to have to add? Well, this flow chart tells us that first of all, you're going to add the lime in the amount of how much carbon dioxide there is. Okay, so we need 55 milligrams per liter of lime to get rid of the carbon dioxide. And remember that we're doing like the unit of currency here is as CaCO3, milligrams per liter as CaCO3. So how much carbon dioxide there is, it may be different than 55 milligrams per liter. It's not 55 milligrams per liter of carbon dioxide. It's 55 milligrams per liter of carbon dioxide as CaCO3. So I'll just point that out again. So we add 55 from the carbon dioxide. Now we need to add as much lime as we've got available for the carbonate. So in our case, that's 277. Okay, next in the flow chart, it asks us, is magnesium more than 40 milligrams per liter? In our case, we have 78 milligrams per liter of magnesium. So yes, that puts us over here. And it says to add how much lime? Magnesium minus 40. Okay, so we're going to add 38 in addition to 55 and 277. But that's not all of it, because we're going to add the 38 from this, and then it's saying is magnesium minus 40, so what we just did, 78 minus 40, is that greater than 40? No. We're no, because it's 38 was 78 minus 40. So 38 is not greater than 40. So now then it says to add just 40 more milligrams per liter of magnesium. No. Okay, so if it was yes, it would put us down there. We were 38, so no, it puts us here into this track. But it is greater than 20. Is the difference minus 40 greater than 20? No, it's not. So we need to add the magnesium amount minus 40. So the leftover magnesium amount that we still have is the remaining 38. So the total amount of lime that's required is the 55 from the carbon dioxide, 277 for carbonate, 38 in the first part of the magnesium here, and then 38 for the magnesium carbonate. And so we need to add 408 milligrams per liter of lime as calcium carbonate. So all of that is to hopefully remove all of the calcium that's present, but then we're only going to be able to get out as much magnesium as we've got carbonate in the system. And we only have 277 milligrams per liter of carbonate. So we need to remove some of the non-carbonate hardness. So over on the whiteboard, we found out that we had 134 milligrams per liter of non-carbonate hardness. And if we're going to figure out how much of the non-carbonate hardness we're trying to remove and find out how much soda should be added, it's going to be 89 milligrams per liter of soda, because the initial non-carbonate hardness was 134, and then the final amount of non-carbonate hardness that we can leave in intentionally is 45, because 40 milligrams per liter is going to be there regardless of what we do. That's just kind of like 40 milligrams per liter is going to be the leftover carbonate component. So the total hardness that remains of 85 is going to include 40 milligrams per liter of carbonate and 45 milligrams per liter of non-carbonate hardness. So that means that the amount of soda that we're going to add is going to be enough to remove we're going to be removing the, if 40 is carbonate is allowed and 45 is the non-carbonate, then we're going to try and remove the magnesium that was here, 78 milligrams per liter. We're going to remove all but 45 milligrams of that. And to do it, we have to add 89 milligrams per liter of soda because of how much non-carbonate hardness there was. Some of the non-carbonate hardness is associated with calcium. In the example that we had here, the carbonate got into the magnesium range, but in this example, the carbonate is only going into a portion of the calcium range, and then the non-carbonate hardness starts even when we've got calcium. So some of the calcium is non-carbonate, and all of the magnesium is non-carbonate. So that's not the only way that we can remove hardness. There are also ion exchange methods for removing hardness. And if you have a home unit of water softening, this is probably what you'd use, is ion exchange. That's what my parents use. They don't have like hydrated lime and that sort of stuff. The way that ion exchange works is that you would try and strip out the calcium and the magnesium from water by replacing it with an equivalent number of charged particles that are sodium. And so, for example, if we had, like in our bar chart example, 333 milligrams per liter of calcium, you can take that out of the water if you replace it with something else. And the idea of ion exchange is that if you replace it with sodium, then you can strip out the hardness because you're maintaining the same overall charge in the solution, but sodium doesn't contribute to hardness because it's a monovalent cation. And so there are these ion exchange resins. They're basically made out of chemicals that calcium is really attracted to the outside of these resin beads, and they can absorb a certain amount of calcium and release the sodium until they need to be occasionally recharged. And so generally once every day or two, you'd have to flush a concentrated sodium solution through that packed column full of resin beads, and then you would waste a certain amount of water, just send it straight to the sewer, that salty brine that's dislodging some of the calcium, and then the water would go, during normal operations, it would trickle through this packed column of the beads, and then as the water is filtering through there, calcium ion is sorbing onto the outside of the resin bead, and it's simultaneously releasing some of the sodium. So that is not generally used on large scale. It's just not commercially viable on a large scale, but you know, for a single home, then ion exchange would be a typical method that's used. All right. So remember that we have no class on Friday, but you do have homework 5 due by 1 o'clock on Friday. So I'll see you next week.